The next two lessons that we cover will be talking about sequences and series. So we'll start with this idea of a sequence. The first thing you need to remember is that a sequence is a function. It actually computes some kind of ordered list. So the example that they're showing you here is the average person in the U.S. uses 100 gallons of water each day. So if you take a look at the function, f of n is equal to 100n. And we can generate terms of the sequence at 100 when n is 1, 200 when n is 2, 300 when n is 3, and so on. And this function actually represents the amount of gallons of water used by the average person after a certain number of days. So it's one person, but multiple days. Another example of using sequences actually involves investing money, which is something that we looked at in the last chapter. So if we had $100 deposited and we get 5% interest compounded annually, so that's once a year, then we actually have this function here where we have $100 and we multiply it by 1.05. So here's your 5% and here's your 100% that you started with to the power of n after n years. So after 1 year we would have 105. After 2 years we'd have 110 and 25 cents. After 3 years, 115 and 76 cents. Again, and we continue onward. There are two different kinds of sequences. We have finite and infinite sequences. A finite sequence has, it uses the set of natural numbers. I'm sorry, my son was picking up toys. Anyway, a finite sequence is a set of natural numbers, right? Natural numbers start at 1. And it goes to some set number, n, as its domain. An infinite sequence is a little bit different because an infinite sequence doesn't end. So if we look at sequences of the natural number multiples of 2, right, 2, 4, 6, 8, 10, and it goes on infinitely. However, the sequence of days in the month of June ends at 30, so that's a finite sequence. So let's take a look at a few sequences that we will try to look at the first few terms. We're actually told to write the first 5 terms for each sequence. So when n is 1, then what we're doing is we're taking a sub 1, which is equal to 5 times 1 minus 2, and a sub 1 is equal to 3. When n is equal to 2, so here we're looking for a sub 2. We have 5 times 2 minus 2, and that gives us 8. When a is 3, we get 13. When a is 4, we get 18. And when a is 5, we get 23. So those would be the first 5 terms of this sequence. However, sequences can be far more complex than this. Another way to organize this would be to make a table. So the value of n and the value of a sub n. So 1, 2, 3, 4, and 5. So again, when a is 1, we're looking at negative 1 to the power of 1 plus 1 times 1 squared. So that's negative 1 squared, which is positive 1, times 1 is 1. We would do it again, negative 1 to the power of 2 plus 1 times 2 squared. So now we're looking at negative 1 to the power of 3, so that's negative 1 times 4 is negative 4. Negative 1 to the power of 3 plus 1 times 3 squared. So negative 1 to the 4th power is 1. 1 times 9 is 9. So here, negative 1 to the 5th is negative 1, times 16 would be negative 16. And then negative 1 to the 6th is positive 1 times 25 is 25. Taking a look at the last one, if n is 1, 3 times 1 plus 2 over 1 squared plus 3, so that's 5/4. And actually what I'll do is I'll just write it here. The next one, 3 times 2 plus 2 over 2 squared plus 3. So that's 8/7. 3 times 3 plus 2 over 3 squared plus 3. So that's 11/12. We have 3 times 4 plus 2 over 4 squared plus 3. So that's 14/19. And then the last one, 3 times 5 plus 2 over 5 squared plus 3 is 17/28. Sometimes when we're looking at infinite sequences, they will tend to get closer and closer to some real number. When we were looking at this in functions, we called it the asymptote. Dealing with sequences, we actually call this a convergent sequence, or say that it converges to some number. So here they're showing you a sub n is equal to 1 divided by n. Well, one of the things that we've looked at in the past is as our denominator gets larger and larger and larger, our graph gets closer and closer to 0, although it never actually touches 0. Not all sequences do this. If you look at this, n squared, right? So whatever your number is, you just square it. As this value of n gets larger and larger and larger, these numbers are going to get infinitely larger too. So we call this a divergent series, meaning that it's going to increase without any boundaries. Now what we've seen already are sequences where we just have a formula or function of some sort and we can just put in whichever number we want to figure out what's happening. Other times we have something called recursive sequence, and what that means is you actually have to know the previous number in order to find out the next number. But what we looked at early on were explicit sequences, where it didn't matter if we knew the previous term or not. So here are some examples using a recursive sequence. We're told that a sub 1 is equal to 2, and that if we're going to find any n, that n that we're looking for has to be greater than 1, so we can't put a 1 here. This first number we can put here would be 2. So when we're listing out the first 4 terms, we know that the first term is 2. So to find the next term, we need 3 times a sub 2 minus 1 minus 1. So we're really looking for a sub 1 minus 1. Well, a sub 1 we found out was 2. So that's 3 times 2 minus 1. So the next term in this sequence is 5. We can do that again with the third term. I need 3 times the second term, which is 5, minus 1, and that gives me 14. And then to find the fourth term, I need 3 times the third term, which is 14, minus 1. And that gives us 41. Looking at the next example, the first term is 5. So the second term is going to be this n minus 1. That's going to be my first term, which is 5, plus 2 times my n, in this case, is 2. So that's 9. A sub 3, I need to take 9 plus 2 times 3. So that's 6 plus 9 is 15. And then to find the fourth term, I need the third term, which is 15, plus 2 times 4. 15 plus 8 is 23. The last problem that we look at is going to be a word problem, and it refers to insects where the population doesn't just grow indefinitely. I'm sure you've remembered this from science class, but it's going to level out at some point because of the natural resources available to sustain it. But what happens is that the population will grow rapidly at first, and then it will level off because of those resources. So here we're looking at the behavior of the winter moth, which is modeled with a sequence that's going to be shown here. A sub n represents the population density in thousands per acre during any given year. So here's the recursively defined sequence for what we're looking for. A sub 1 is simply 5. To find a sub 2, we need 2.6 times the number before it minus 0.25 times that same number squared. And that will give us about 6.75. We do that again. 2.6 times 6.75 minus 0.25 times 6.75 squared, and that will give us about 6.16. .6 times 6.16 minus 0.25 times 6.16 squared is going to give us about 6.53. .6 times 6.53. Sorry, that's terrible 3. Minus 0.25 times 6.53 squared will give us 6.32. And then the last one of this sequence, 2.5 times 6.32 minus 0.25 times 6.32 squared will give us about 6.45. What I hope that you've noticed is that these numbers are oscillating, right? So up, then down, then up, then down, then up. What's happening to the population as this value increases is that it's going to oscillate about some value. Now what I do is I take the mean of every pair. So if I take the mean here, I would get 5.875. When I take the mean here, I get 6.64. Then I take the mean here, and actually I calculated this wrong. It's 6.455. So now I take the next mean, 6.16 and 6.53, and I get 6.345. Do that again with this pair of numbers, and you get 6.425. And then the last time with what we've got, and you get 6.385. So if you look at these values, they're actually getting closer and closer to about 6.4. So as the population density increases, this population is likely to stabilize near 6.4 thousand. Per acre.